We start off with basic definitions. In algebra, groups, rings, fields, and vector spaces. So groups are a set with associative binary operation, identity, and inverses. And rings are defined like this. A set R which has two operations, addition and multiplication. If R is a commutative ring with a unit element and non-zero elements of R form an abelian group under multiplication, we call R as a field. There's also something called as finite fields, which is field with finite number of elements. A field is also called as a division ring, a commutative division ring, or a skew field, commutative skew field, because a division ring is a ring where the non-zero elements gets grouped under multiplication. There's also something called as a zero division ring, where if R is a commutative ring and A and B are not equal to 0 and A and B product equals 0, we call R as a zero division ring. In integral domain, either A has to be 0 or B has to be 0 for the product of A and B to be 0. So there are no zero division rings in integral domain. We then go on to homomorphisms. Homomorphism is a mapping such that phi of A into B equals phi of A into phi of B, and phi of A plus B equals phi of A plus phi of B. So phi is a homomorphism of R into its mirror image R dash. So if that's true, then phi of 0 equals 0 and phi of minus A equals minus phi of A. We then go on to kernels. So if phi is a homomorphism of R into R dash, then the kernel of phi we represent it as I of phi. So then phi of A equals 0. A kernel is elements which are mapped to 0. They are closed under addition and multiplication. It contains the 0 element and it has additive inverse. There are different types of homomorphisms. There are zero homomorphisms, identity homomorphisms. There's even isomorphism. Zero homomorphism is when phi of A equals 0. Identity homomorphism is when phi of x equals x and the kernel of phi is a 0 set. Isohomomorphism is when two rings have the same structure almost, and isohomomorphism is bijective plus homomorphic. When when a function is mapped from R to R dash, phi is onto, and if the kernel of phi is 1 1, we call it bijective, and thus R to and R dash is homomorphic. We then go on to the concept of ideals. Ideals are denoted by a capital U. So they are an additive subgroup of R which are closed under addition and absorbs multiplication from both sides. Quotient rings are denoted by R by U, and they are denoted as A plus U where A belongs to R, and A plus U can be represented as A plus I where I belongs to the coset of U. AB in R is equivalent if A minus B belongs to U. We then go on to maximum ideals. A maximum ideal is an ideal which is as large as possible without being the entire ring. So M is a maximum ideal if M is not equal to R and there is no ideal in U such that there is no other set between M and R. That's when M is called as a maximum ideal. We then go on to polynomial rings. Polynomial rings are denoted by a capital F of X, where F is field and F of X denotes ring of polynomial with coefficients from field. There is the division algorithm in F of X, which states F of X equals q of x into g of x plus r of x, and the degree of r of x is lesser than the degree of g of x. We then learn about irreducible polynomials. If, let's say, an irreducible polynomial p of x exists, then p of x cannot be factored into non-constant polynomials over f. So p of x can be written as a of x into b of x. So either a degree of a equals 0 or the degree of b equals 0. The irreducibility will depend upon the field. We then have the Gauss lemma, which says that a primitive polynomial, which means the GCD is 1, with integer coefficient is reducible over q, is also reducible over z. So if we were to find the irreducibility over q, we have to first check the irreducibility over z. Then we have homomorphic encryption types. We have partially homomorphic encryption, we have fully homomorphic encryption, and we have leveled homomorphic encryption. So partially homomorphic encryption is also called PHE. It supports only one operation, either addition or multiplication, but never both. So if it supports only addition, what the example we have learnt of is pilear, which is additively homomorphic. If it supports only multiplication, an example is elgamal, which is multiplicatively homomorphic. Next we have fully homomorphic encryption. It supports both addition and multiplication. One example is Gentry's FHE scheme. Next is leveled homomorphic encryption or LHE. It supports both addition and multiplication, but only at a limited level. We then go deeper into the pilear GSW CKKS schemes. So first is pilear encryption. In pilear, the public key is the multiplication of two large prime numbers p1 and p2, and secret key is p1 minus 1 into p2 minus 1. There is the encryption, and there is the encoding, then there is the encryption, decryption and decoding steps given below. We then go on to GSW scheme. In GSW scheme, the secret key is sampled from ZQN space. There is again encoding, encryption, decoding and decryption. In GSW, noise comes into picture, so we call noise as bound noise B, and we refer to ZQN, that Q, we refer to Q as ciphertext space. It is usually 10 to the power 20 or 10 to the power 15. It's a very large number. We then go on to CKKS. Here the secret key is sampled from -101 power n. We have few additional steps in CKKS. There is encoding, there is relinearization, there is rescaling, decoding and decryption. The steps are given below. After CKKS, we have covered the topic of secret sharing and oblivious transfer, which are different types of methods to encode or encrypt data securely. We first go on to secret sharing algorithm. In secret sharing, data is split into s greater than or equal to 2 shares. So at least if we have L from 2 to S, L is the number of shares required to reconstruct the message completely. So L comma S is going to be the threshold scheme. Here we have learned 2 comma 2. So L is 2 and S is also 2. S is the upper bound and the total number of shares, and L is a threshold from which we take the number of shares. Here we use random number to mask the message into an encoded format and then remove that random number in reconstruction of the message. We then go on to oblivious transfer. So oblivious transfer can be understood by an example. If A has two messages M0 and M1 and wants to send only one to B, and B does not want A to know which one he receives, we use oblivious transfer for that. Oblivious transfer can be implemented using Pylear. It can also be implemented using LGML. So below is the implementation using Pylear and the steps given. We then have encrypted linear control. We first start off with what is linear control. Control law comes into the picture, which is uk equals k into x of k. uk is the control input, k is the control gain matrix, and x of k is the state matrix. If it were in a discrete time linear system, we get x k plus 1 equals a x of k plus b u of k. A is the state matrix, b is the input matrix. There is also an output equation y equals c x of k plus d u of k, where c is the output matrix and d is the feed forward matrix. But that will be discussed in detail a bit later. So the concept of encrypted linear control is to get u of k, the input, control input, without decrypting x of k, the state input. So we can do it two ways. We can do it using LGML implementation, and the second can be done through RSA technique. But only in this case, using RSA is a little more insecure, but if we do padding, it will be more secure. Let's discuss LGML implementation. It can be classified roughly into 3 steps. So step 1 will be state encryption. X of k will get encrypted to x bar of k, or encryption of x of k. Step 2 is computation in cloud. This is where the control law comes into picture. U of k is equal to k into x of k, but if encryption of u of k is equal to encryption of k into encryption of x of k, it is done using the multiplicative homomorphism of LGML implementation. Next, step 3 happens at the actuator. There is something called as communication overhead in this. So instead of sending m control values, the cloud, which does the computation of the control input, encrypted control input, sends m cross n ciphertext. So the actuator does the decrypting, and when it decrypts m cross n elements of u of k, the computational overhead will be very high. There are also some other demerits of LGML encryption scheme. There could be overexposure at actuator, since it is decrypting it and we are getting the plain text values there. And also because since LGML is only multiplicative HE, we don't have any additive HE. One of the few merits is that the controller gain matrix K, it remains private throughout the cycle. Moving on to encryptive model predictive control. This is done by solving optimization problems, or OCP. So the optimal control problems are converted into quadratic problems and then solved. So here z star of x is a piecewise affine function of x. Affine function is a function which is like ax plus b. So if we apply it in like control law, you get u of k equals k x of k plus b. So k is gain matrix, x of k is input, b is called as bias or offset. So that can be an example of a find function. So there are two methods for implementation of encrypted model predictive control. First is the offline optimization and second is the online optimization. In the offline optimization, the state space is mapped onto a polyhedron with V regions, and each region has a control law uk equals k x of k plus b and a find function. A polyhedron is an object which has multiple dimensions, and it is also called as the intersection of finite number of half spaces. So half space is ax lesser than or equal to b. So each row of that is a half space. So now when the state space gets mapped to a polyhedron and each region has a control law, we have to first compute u of k. So we have to first correspondingly we have to evaluate the affine function. Then we are going to be encrypting it since it's encrypted model predictive control, where we'll encrypt u of k equals k x of k plus b, maybe using pilear. This computation is done in cloud and the encrypted u of k is given to actuator. The actuator decrypts it and gives the decrypted u of k back. But what exactly happens is in offline optimization, u of k is actually pre-computed for each region in the polyhedron, and the polyhedron, if it has some sigma segments, and x of k lies only in one region of this polyhedron, we have to apply the control law and the region needs to be identified. In order to identify the region, you can do it in two methods to find out where x of k is. First, either the sensor identifies the current active region and gives cloud the correct sigma, or the cloud evaluates u of k for all the sigmas and the actuator receives all and decrypts all. So the computational overhead again increases. That's it for offline optimization. We now go to online optimization. In online optimization, real-time iterations is what is happening. So encrypted model predictive control, we are solving using fast projected gradient scheme, or what I have used is fast gradient method in my project. In online optimization, there is something called as Z0 of k, which is encrypted initial guess. So at step k, the sensor sends this encrypted initial guess plus x of k, which is the state, to the cloud. And this initial guess is solved using gradient descent. So real-time iterations happen like this. They start from the previous solution or the initial guess, and then the iterations happen, and then they send back the updated encryptive control or control action. So it's a proper loop. In online optimization using MPC, what happens is that it offloads the optimization to the cloud, unlike in offline optimization. While offloading the optimization to the cloud, we can use two non-colluding clouds, wherein each cloud has a partial information and they don't collaborate, and both run the MPC protocol, and no one cloud can fully reconstruct the input. So the overall flow for online optimization can be said like this. So the sensor encrypts the Z0, which is the initial guess, plus x of k, the state. It sends it to the cloud, two clouds, and the two clouds perform projected gradient and either using secret sharing or homomorphic encryption, and they get the output u of k. This u of k goes to the actuator to get decrypted and it goes back to the control. There are also different types of encrypted control depending on the number of subsystems. We have encrypted distributive control, which is for many subsystems. Then we have encrypted cooperative control, which states that when M agents are there, there are M crypto systems. There are three steps in encrypted cooperative control. Step 1 is the control shares. Instead of U of k, what we do before, now V of k equals k into x. So at agent j, U of k equals an affine function, which is V of k plus an increment of V of k. This U of k hides the local states from agent I, but agent j can still access k and v. So we do homomorphic multiplication or homomorphic addition, and through computation we get u of k back again or v of k back again. So what cooperative control does is, instead of providing the control input, it provides the aggregate share to agent I so that it doesn't guess what is the amount of share or the input which was originally given. We now come to secure multi-party computation for cloud-based control.